Ever scroll through your camera roll and wonder, like, how do computers actually see these photos?
Mm-hmm.
Sure, we get the whole pixel thing.
Yeah.
But today, we're diving deeper.
Yeah.
Way deeper.
Into the matrix.
Into the world of image processing and this foundational technique called image thresholding.
Oh, it's more than just foundational. It's everywhere. Think medical imaging, self-driving cars, even those filters you use on social media.
Right.
Image thresholding is working behind the scenes.
Okay, so less about the cute dog pics.
Yeah.
More about the tech that makes those kicks meaningful to a machine.
Mm-hmm.
From what I've gathered from these research papers, it's surprisingly complex.
You're right. It's not as simple as it sounds. At its core, image thresholding is about simplifying an image.
Yeah.
But it's also about making crucial decisions about what information to keep and what to discard.
Interesting.
Imagine a sculptor chipping away at a block of stone. They're not just randomly removing pieces.
Right.
They're carefully choosing what to remove to reveal the form within. That's what these algorithms are doing with images.
Wow.
But instead of chisels, they're using math.
Okay, so it's like a sculptor having to make those decisions
Exactly.
about what's important and what's not, but instead of a hammer and chisel,
Right.
they're using algorithms and code and all that.
Exactly.
And just like a sculptor needs different tools for different tasks,
Mm-hmm.
there's a whole buffet of image thresholding techniques,
Yes.
each with its own strengths and weaknesses.
Exactly. And the choice of which technique to use can have huge implications in the real world.
Oh, wow.
For example, in medical imaging, if the thresholding isn't precise, it could mean the difference between identifying a tumor accurately
Right.
or missing it completely.
Wow.
There was this one case study we reviewed.
Whoa, hold on. Before we get too deep into the case studies, let's
Right.
back up a bit.
Okay.
I want to make sure I'm really wrapping my head around the basics here.
Okay.
We've got single thresholding and multi-thresholding, right?
Yes.
What's the deal with those?
Great question. Think about it like light switches.
Okay.
Single thresholding is like your basic on-off switch. It divides the image into two categories, black and white, based on a single brightness level.
Mhm.
Fast, efficient, doesn't require a lot of computing power. Essential for things like mobile devices where resources are limited.
Makes sense. But I imagine there are times when you need more than just an on-off switch.
Mm-hmm.
That's where the multi comes in.
You got it. Multi-thresholding is like having a dimmer switch. Instead of just black and white, you can have multiple levels of gray. This is crucial for more complex images where you need to capture subtle details, like those used in facial recognition software.
So it's a trade-off, right?
Mm-hmm.
Speed and simplicity
Yeah.
versus detail and accuracy.
Exactly.
Now that we understand that basic trade-off, let's explore those sculpting tools. Those techniques you mentioned earlier. The research papers mention a whole bunch of them. Otsu's method, Kittler, and Illingworth's minimum error thresholding. Potential difference. It's a mouthful.
It is. And each of these techniques has its own personality, so to speak.
Right.
They all aim to find the best threshold values,
Mm-hmm.
but they go about it in different ways.
Can we break down a couple of those?
Sure.
Just, I'm not lost in a sea of technical jargon.
Right.
For instance, potential difference sounds more like a physics lesson than image processing.
It does, doesn't it?
Yeah.
It's actually based on an analogy to electrical potential.
Okay.
Imagine the different brightness levels in the image as having varying electrical charges. It's a way to measure the contrast between different regions in the image. Then you have Kittler and Illingworth's minimum error thresholding.
Mm-hmm.
It sounds intimidating,
It does.
but the goal is simple: minimize mistakes.
Okay.
This method aims to find the threshold that results in the fewest classification errors,
Right.
which is critical for applications like recognizing handwritten text.
Okay, that one actually makes sense.
Yeah.
Minimize errors in reading bad handwriting.
Exactly.
Crucial. But what about these newer approaches?
Okay.
What makes them stand out from the classics?
Well, many of them are focused on multi-level thresholding, taking advantage of those dimmer switches we talked about.
Right.
They aim to select multiple threshold values to capture even more subtle differences within an image.
So even more nuance.
Exactly.
Even more like how our own eyes work.
Exactly. And one method in particular caught my eye.
Okay.
It uses something called the peak signal-to-noise ratio, or PSNR.
Okay, I'll bite. Peak signal-to-noise ratio. Lay it on me.
Think of it like this. You want to make a digital copy of a physical photograph.
Okay.
The PSNR would be a measure of how closely that copy resembles the original. A higher PSNR means a better quality copy.
Okay.
Researchers are using the same principle to find the best threshold for images, trying to maximize the similarity between the original image and its simplified thresholded version.
So it's like finding the sweet spot for audio compression, right?
Yes,
You want to make the file smaller without losing too much audio quality.
precisely. And just like with audio compression, different approaches work better for different types of images. Some methods are better for high contrast images. Others excel at handling detailed textures.
Okay.
You know, like those old crinkled photographs we cherish.
Right, right. So just like those old photographs, each image presents its own unique challenges. Speaking of challenges, these research papers mentioned using real-world data sets to test these methods.
Right.
One in particular caught my eye, something called DIBCO.
Ah, the DIBCO benchmark.
Yeah, is that?
It's like the ultimate proving ground for these algorithms.
Okay.
It uses a massive collection of handwritten and printed documents. You know, the kind of stuff even humans struggle to read sometimes.
Oh, tell me about it. My doctor's handwriting is practically its own cipher.
Exactly.
Yeah.
So you can imagine how challenging it is for a computer to accurately threshold those images, but that's precisely why DIBCO is so valuable.
Right.
It helps researchers evaluate how well different techniques perform under pressure.
So what did they find? Any clear winners after putting them through the DIBCO ringer?
It's funny you should ask.
Yeah.
What they discovered is there's no one-size-fits-all solution. Just like you wouldn't use a wrench to hammer in a nail.
Right.
Certain methods are better suited for certain types of images. Some excelled at deciphering handwritten text.
Okay.
Others were better at recognizing edges in those crinkled photos we talked about.
Right.
It really highlights the need for the right tool for the job.
Horses for courses, as they say.
Exactly.
But beyond DIBCO, weren't there some other interesting data sets?
Yeah.
Didn't I see something about license plates?
Absolutely. License plate recognition is another area where image thresholding is essential. Think about those automated toll booths or security cameras that scan license plates. They need to be incredibly accurate to work reliably.
Right.
The researchers used images of Malaysian vehicle license plates to test how well these techniques could identify the characters, even with different fonts, lighting conditions, and even dirt obscuring the plate.
Wow. So real-world messy.
Real-world messy.
That makes a lot of sense.
Yeah.
I'd never really considered the complexity involved. It really is amazing how far this technology has come.
It really is. And it's still evolving.
Really?
In fact, one of the papers explored a completely different approach to thresholding, one inspired by, of all things, ants.
Okay, now that's just cool.
Yeah.
Ants?
Ants.
As in the tiny insects crawling around on the sidewalk?
Yeah.
How in the world?
I know, right? It sounds crazy, but it's called ant colony optimization, or ACO. You see, ants are surprisingly good at finding the shortest path to a food source.
Yeah, I've seen them forming those little trails. It's like they have a map or something.
They do, in a way.
Yeah.
They leave behind pheromone trails, and the more ants that follow a particular path, the stronger the scent becomes, signaling to other ants that it's an efficient route.
Okay.
Yeah.
Okay, I'm following so far. But how does that translate to processing images?
So, researchers essentially unleashed virtual ants onto digital images. Imagine the image as a landscape, and these ants are sniffing out the strongest edges, leaving behind their digital pheromones. The more ants that converge on an edge, the more defined it becomes, allowing the algorithm to determine where to apply the threshold.
So they're basically using the ants' natural behavior to help computers see the most important boundaries within an image. That's brilliant. It got of weird, right? Using ants to help computers see.
Definitely outside-the-box thinking. And the results were impressive. This ant-inspired approach showed real promise, especially when dealing with those complex images that often trip up other methods. But beyond the specific techniques, the research also highlighted some broader takeaways.
Oh, like what?
Well, remember how we talked about horses for courses? That's one of the big takeaways here. There's no single best way to threshold an image.
So no magic bullet, unfortunately.
Exactly. The key is to choose the right method based on the specific image and what you are trying to achieve. But perhaps the most exciting takeaway is that the future of image processing is likely to be adaptive.
Adaptive? Does that mean our computers will be out here evolving on their own? Sounds a bit Terminator-esque, if you ask me.
Haha. Not quite. But imagine algorithms that can adjust their thresholding parameters on the fly, depending on the specific content of an image or even changes in lighting conditions.
Okay, so less Arnold Schwarzenegger, more like our own eyes adjusting to different environments.
Exactly. Think about it. Our eyes don't just see in black and white or even shades of gray. They adapt to subtle variations in color, contrast, and brightness, allowing us to see clearly in a wide range of conditions.
Right.
That's the kind of dynamic adaptability researchers are trying to replicate in image processing algorithms.
So instead of static algorithms,
Right.
we're moving towards a world where image processing is as dynamic and responsive as our own vision.
Right.
That's kind of mind-blowing when you think about it. It really is.
Yeah.
This idea of adaptive image processing has the potential to revolutionize everything from medical diagnoses to the way self-driving cars navigate the world around us.
Right.
Imagine a world where medical scans could automatically adjust for differences in patient anatomy or tissue density, leading to more accurate diagnoses. Or imagine self-driving cars that can see clearly, even in challenging weather conditions like heavy rain or fog.
We're talking about a whole new level of safety and efficiency.
Exact.
Not just for cars,
Right.
but for all sorts of applications. But this all circles back to what we were discussing earlier about the importance of choosing the right tool for the job.
Right.
As these algorithms become more adaptable, that decision-making process becomes even more critical.
Absolutely. And it's not just about technical considerations.
Right.
We also need to think about the ethical implications of this technology.
Because as image processing becomes more sophisticated,
Right.
it becomes harder to distinguish between what's real and what's been digitally enhanced or even altered entirely.
Right. It raises important questions about authenticity, trust, and even the nature of reality itself.
Wow.
Think about those deepfake videos that have become increasingly difficult to detect.
It's a bit unnerving, to be honest.
Yeah.
We're entering a world where we can't always believe what we see, even with our own eyes.
It's true. And it highlights the need for critical thinking and media literacy.
Right.
We need to be aware of the potential for manipulation and be cautious about the information we consume. But this isn't just about being skeptical. It's also about appreciating the incredible power of this technology and its potential to improve our lives.
It's like any tool. Right.
Exactly.
A hammer can be used to build a house,
Right.
or it can be used to cause harm.
Yeah.
It all depends on the intent of the user.
Exactly. Image processing at its core is about extracting meaning from visual data.
Yep.
And as we've seen, there are countless ways to do that, each with its own set of strengths and limitations. The key is to use this technology responsibly and thoughtfully, always being mindful of its potential impact on individuals and society as a whole.
Wow, this has been an incredible deep dive. We've gone from the basics of how computers see images all the way to the ethical considerations of increasingly sophisticated algorithms. It's amazing to think that something as seemingly simple as converting an image to black and white can be so complex and have such far-reaching implications.
It really goes to show that even in a world increasingly dominated by artificial intelligence, human judgment and insight are more important than ever.
Couldn't agree more. So to our listener, we leave you with this. The next time you encounter an image, whether it's a medical scan, a photo on social media, or even just a street sign captured by a self-driving car, take a moment to appreciate the intricate world of image processing that's at play. And remember, the more you understand about how these technologies work, the better equipped you'll be to navigate our increasingly complex digital landscape.
And never be afraid to ask questions. Curiosity is the key to understanding.
Right.
And ultimately to harnessing the power of these technologies for good.
Well said. Until next time, keep exploring, keep questioning, and keep diving deep.